Based question from the lesson Electrochemistry. In the plot of molar conductivity versus square root of concentration, following curves are obtained for two electrolytes A and B. Predict the nature of electrolyte A and B. What happens on extrapolation of lambda m to concentration approaching 0 for electrolyte A and B. Here, A is strong electrolyte because in the case of A, the molar conductivity increases slowly with the dilution. So, the electrolyte A is strong electrolyte and B is weak electrolyte because in the case of B, we can see a steep increase in molar conductivity with the dilution. Strong electrolyte, the lambda m value increases slowly with the dilution because strong electrolyte undergo complete dissociation initially, but with the dilution the interionic interaction decreases and the mobility of the ion increases. As a result of this, we can see a slight increase in molar conductivity. But in the case of weak electrolyte, the molar conductivity increases steeply because the degree of dissociation of weak electrolyte increases and the number of ions per unit volume also increases. So, molar conductivity increases steeply. Second part of the question, what happens on extrapolation of lambda m to concentration approaching 0 for electrolyte A? When we extrapolate the graph for strong electrolyte, it will meet the y-axis and you will get the intercept lambda m0. That is known as limiting molar conductivity. That is the molar conductivity at 0 concentration. So strong electrolyte, when we extrapolate, it will meet the y-axis and we will get the intercept lambda m0. But for weak electrolyte, we know the graph is going steeply and it is going parallel to y-axis. So even though we extrapolate, it will not meet the y-axis, it will go parallel to y-axis. As a result, we cannot find out the limiting molar conductivity from the graph. Second question, the curve V is for KCl or acetic acid. So in the previous question we saw the curve V is for weak electrolyte. So here acetic acid is the weak electrolyte. And what is the intercept on lambda m axis for x equal to? Intercept means when we extrapolate the graph will touch the y-axis at a point, that is at 0 concentration the molar conductivity will be limiting molar conductivity. So what is the intercept on lambda m axis of x equal to? That is equal to lambda m 0, that is the limiting molar conductivity. Give the mathematical equation representing a straight line. So for strong electrolyte, we can write the straight line is for strong electrolyte. Lambda m is equal to lambda m0 minus a into c raised to 1 by 2, or we can write a root c. Now, what is the slope equal to? This equation is of the form y equal to mx plus c. So the slope is equal to minus a. So we can write slope is equal to minus a. What happens to molar conductivity on dilution in the case of weak electrolyte and why? On dilution, for weak electrolyte, the degree of dissociation increases. So the number of particles increases with the dilution, and also the interionic interaction decreases and the mobility of the ion increases. So the molar conductivity increases steeply with the dilution. But the graph is going parallel to y-axis and it will not intersect the y-axis. So we cannot calculate the limiting molar conductivity from the graph. Now, next question. The molar conductivity of acetic acid at infinite dilution is 390 Siemens centimeter square mole raised to minus 1. Using the graph and given information, the molar conductivity of CH3COOK will be. So, CH3COOK, the salt is formed by combining acetic acid with a KCl. CH3COOK is equal to CH3COOH plus KCl. So we can take the sum of the molar conductivity of these two, and from that we can subtract the limiting molar conductivity of HCl. So limiting molar conductivity of acetic acid is given in the question as 390 Siemens centimeter square mole raised to minus 1. And from the graph we can find out the limiting molar conductivity of HCl, that is 425, and KCl as 150. It is between 175 and 125, so we can take it as 150. So limiting molar conductivity of acetic acid we know, HCl we know, and KCl also we know. So to calculate the limiting molar conductivity of CH3COOK, we can take the sum of the limiting molar conductivity. According to Coldrash's law, the limiting molar conductivity is sum of the conductivity of cation and anion. So we can take limiting molar conductivity of CH3COOH plus the limiting molar conductivity of KCl minus, now the unwanted ions we can subtract, limiting molar conductivity of HCl. So that is equal to 390 plus 150 minus 425. 390 plus 150, 540 minus 425. So that will be equal to 115. So our option is B. 115 Siemens centimeter square mole raised to minus 1. The following figure represents variation of molar conductivity versus square root of concentration for an electrolyte. Here lambda m is the molar conductivity and C is the concentration of the electrolyte. Define molar conductivity, identify the nature of electrolyte on the basis of the above plot, determine the value of limiting molar conductivity, show how to calculate the value of A for the electrolyte using the graph. Here, let us see the graph, and before that, let us define molar conductivity. Molar conductivity of a solution at a given concentration is the conductance of the volume V of solution containing 1 mole electrolyte kept between two electrodes with the area of cross-section A and distance of unit length. Here, we have to identify the graph. It's a straight line graph and the slope is negative slope, and also the graph is touching the y-axis, and we are getting the molar conductivity at zero concentration, which is known as the limiting molar conductivity. And the electrolyte, we can see the molar conductivity increases slowly with the dilution. Because of that, the electrolyte is a strong electrolyte. The electrolyte is strong electrolyte. Determine the value of limiting molar conductivity. So the graph is touching the y-axis and you will get the intercept lambda m0. So lambda m0 at zero concentration is known as limiting molar conductivity. Molar conductivity at zero concentration is known as limiting molar conductivity. Show how to calculate the value of A for the electrolyte using the graph. So A means slope of the graph. That is, this for strong electrolyte we can write the equation lambda m is equal to lambda m0 minus A root C. So here slope is negative A, or A is equal to negative slope. Now let us calculate the slope from the graph. So let us take a particular point, that is molar conductivity against concentration. So 149 corresponding concentration let us take. Similarly, for 147.8, let us calculate the concentration. So here y2 minus y1 by x2 minus x1. y2 minus y1 divided by x2 minus x1. Slope is equal to y2 minus y1 by x2 minus x1. Now y2 is 147.8 minus y1 is 149 and x2 is 0.022 minus x1 is 0.010. So when we take the difference equal to minus 147.8 minus 149, that will be minus 1.2 divided by 0.022 minus 0.010, that is equal to 0.012. So that is equal to 1.2 by 0.012, that is equal to 100. So our slope is equal to 100 Siemens centimeter square mole raised to minus 1 divided by mole per liter raised to 1 by 2. The figure carefully which statements are correct. In the figure we can see external potential is greater than 1.1 volt. That is, the potential of Daniel cell is 1.1 volt. We are applying an external potential which is greater than 1.1 volt. Then the cell will work like an electrolytic cell. Now let us see the options. Electron flow from copper to zinc and current flows from zinc to copper. That statement is correct statement. Zinc is deposited at zinc electrode and copper dissolves at a copper electrode. That's also correct. The cell acts as an electrolytic cell. That's correct statement. So our option is all of this. All the above statements are correct. The resistance of an electrolyte measured by conductivity cell is shown in diagram. This cell uses AC current, DC current, either AC or DC, no current. So we know if you are using direct current, the composition of the electrolyte will change. That is, the electrolyte will undergo electrolysis. Because of that, we cannot use direct current, so we have to go for alternating current. So we are using AC current. Now, next question is from D and F block elements. Based on the graph, why manganese has lower melting point than chromium? So manganese, we know the electronic configuration of manganese is 4s2 3d5, whereas the electronic configuration of chromium is 4s1 3d5. So in the case of manganese, the d orbitals are singly occupied and 4s orbital is completely filled, and this 3d electrons are tightly held by the nucleus and the electrons are not available for bonding. So it takes part in weak metallic bonding only compared to chromium. The metallic bonding in manganese is weaker. Because of that, its melting point will be low. Then, second question, why do transition metals of 3D series have lower melting point as compared to 4D series? In 4D series and 5D series, the heavy transition metals, we can see frequent metal-metal bonding. So that we can see in heavy transition metals compared to 3D. That is why 3D has lower melting point and 4D and 5D has higher melting point. Now, the third question, in the third transition series, identify the name of the metal with a high melting point. So here this metal is tungsten only. Tungsten is having highest melting point in the third series. So the element is tungsten. Next question is from coordination chemistry. The above splitting of d orbital takes place in the formation of, we know, the degenerate orbitals. When ligand approaches, it is split into two sets, T2G and EG. Here EG has higher energy than T2G, and this splitting and the difference in energy is delta O. This happens in octahedral complexes. So our option is C.